In the last class, we have derived energy of a particle confined in a one-dimensional potential well as En equal to n square h square divided by 8 ml square, where n is the principal quantum number for the energy state, that is n is equal to 1, 2, 3, etc. We have derived the normalized wave function psi n equal to root of 2 by L sin n pi x by n. And we have to see what happens when n equal to 0. When n equal to 0, psi n equal to 0 and the probability density psi n square equal to 0. Psi n square equal to 0 means the probability density, that is the probability to find the particle inside the box, is 0. That is, n equal to 0 is ruled out because the particle is already present inside the box. Let us see what happens when n equal to 1. When n equal to 1, E1 equal to h square divided by 8 ml square, and the corresponding wave function psi 1 equal to root of 2 by L sin pi x by L, and the probability density function psi 1 square equal to 2 by L sin square pi x by L. At x equal to 0 and x equal to L, mod psi 1 square becomes 0. That is, at x equal to 0, sin square term is 0, and at x equal to L, this term becomes sin pi. So, mod psi 1 square equal to 0 at x equal to 0 and at x equal to L, which implies the probability to find out the particle at x equal to 0 and at x equal to L is 0. But at x equal to L by 2, what happens? At x equal to L by 2, mod psi 1 square equal to 2 by L sin square pi into L by 2 divided by L. That is, this term becomes sin square pi by 2. That is, mod psi 1 square has the maximum value. Mod psi 1 square has the maximum value, which implies the probability of the particle to find out the particle inside the box is maximum at the center of the box. If we draw a graph of probability density function versus x, that is mod psi 1 square and x. So at x equal to 0 and at x equal to L, that is, this is the one-dimensional box and the width of the box is L. So at x equal to 0 and at x equal to L, probability to find out the particle is 0. And at x equal to L by 2, the probability to find out the particle is maximum. That is the graph like this. That is, at x equal to L by 2, the probability equal to maximum. And at x equal to 0, the probability to find out the particle is 0, and at x equal to L, the probability to find out the particle is 0. So this is the case when n equal to 1. Next, when n equal to 2. When n equal to 2, the energy E2 equal to 4h square divided by 8 ml square, that is 4E1. And the corresponding wave function psi 2 equal to root of 2 by L sin 2 pi x by L. And the probability density function equal to 2 by L sin square 2 pi x by L. At x equal to 0, x equal to L by 2 and x equal to L, let us see what happens. At x equal to 0, this term becomes 0, and at x equal to L by 2, this term is sin n pi terms, and at x equal to L also sin n pi term, that is mod psi 2 square equal to 0. which implies the probability to find out the particle at x equal to 0, x equal to L by 2 and x equal to L equal to 0. And at x equal to L by 4 and at x equal to 3L by 4, the probability to find out the particle has the maximum value. If we plot a graph like this, that is mod psi2 square and Ex. So, at x equal to 0, x equal to L by 2 and x equal to L, the probability density function has 0 value, and at x equal to L by 4 and at x equal to 3L by 4, the probability function has the maximum value. So, the graph like this. That is at x equal to L by 4 and at x equal to 3L by 4, mod psi2 square has the maximum value. That is the probability to find out the particle at this point has maximum. Similarly, we can draw n equal to 3, n equal to 4, etc. So, the possible energy values are E1, 4E1, 9E1 and 16E1, etc. That is, a particle confined to a box can't have any arbitrary values of energy, but only certain discrete values. And the different values of energy are called eigenvalues, that is energy eigenvalues. So, this is the problem of particle confined in a one-dimensional potential well. Next, we have to discuss tunnel effect, that is quantum mechanical tunneling. So, according to classical mechanics, when a particle of kinetic energy E approaches a potential barrier of V0, that is if E less than V0, it reflects back without entering the other side. So, consider a potential barrier of height V0. Suppose an electron with a mass Em and the kinetic energy E, that is less than V0, it approaches the potential barrier. According to classical mechanics, it reflects back without entering the other side. This is the classical picture. If we consider electron as a wave in case of quantum mechanical structure, so this is V0, the potential barrier, and if we consider the wave behavior of electron, so there is a finite probability to tunnel through the barrier. This is the quantum mechanical picture. So, in quantum mechanics, the wave function representing the particle does not vanish on the other side of the barrier. That is, there is a finite probability of the particle to penetrate through the barrier even when E less than V0. This is called tunnel effect. That is, if we consider the potential barrier like this, that is, this is region 1, this is region 2 and this is region 3. So, if we consider the particle as a wave, there is a finite probability to tunnel through the barrier. That is tunnel effect. This is the height of the potential V equal to V0 and V equal to 0 in region 1 and region 3. So, this is the tunnel effect.